Hi, welcome back to es346 Basic Thermodynamics. This is module 7.6, Isentropic Ideal Gas Processes. And the section in the textbook is section 7.9. Here are the two learning outcomes of this module. At the end, you will understand the three isentropic relations for ideal gases, and you'll be able to calculate property changes during an isentropic process of an ideal gas. So first I want to go ahead and derive the isentropic property relations, starting from the TDS relationships. And so here I show the first TDS relationship. And just to remind you, isentropic simply means that delta S is equal to 0, or the entropy is a constant. Therefore, from this TDS relationship, I can set that whole term equal to 0 for a process in which the entropy does not change. I can then go ahead and rearrange this equation here, and if I move one to the other side, I get ln of T2 over T1 is equal to minus R over C sub V, ln of V2 over V1. Now I'm going to go ahead and do some other further substitutions. And one I'm going to use is this value K, which is defined as simply the ratio of the heat capacities, Cp over Cv. And it just makes this form get a little bit simpler. And I'm also going to use another relationship, which is for ideal gases, Cp minus Cv is equal to R. So the value of R is the difference between those two. And if I go ahead and use those two and do some simple algebraic manipulation here, I can turn this equation into another form that says T2 over T1 is equal to V1 over V2 to the exponent of K minus 1. Okay? So what this relationship does is it tells me, for example, how the temperature changes with the volume as long as the entropy remains constant. Let's go ahead and do another relationship. This time I'm going to use the second TDS relationship, and again for an isentropic process, so I'm going to go ahead and set that equal to 0. So again, remember in these things, K is defined as Cp over Cv, and Cp minus Cv is equal to R. Now, if I go ahead and rearrange this equation, I get ln of T2 over T1 is equal to R over Cp, ln of P2 over P1. And again, some algebraic manipulation here lets me go ahead and rewrite this as T2 over T1 is equal to P2 over P1 to the exponent of K minus 1 over K. And so I've got another relationship. Now it's telling me how the temperature changes with pressure during an isentropic process. And if I combine those two relationships, so both of them had T2 over T1 equal, if I go ahead and set those two things equal to each other, I can get this relationship, which says P2 over P1 is equal to V1 over V2, and that's to the power of K. So I have three relationships now, three isentropic relationships. One is a TV pair, one is a TP pair, and one is a PV pair. They all do the same thing. They describe how ideal gases behave during isentropic processes. It's really just a matter of which one of those pairs do I care about for which one of those tools that I go ahead and use. So let's go ahead and do an example here. And what I'm going to look at is a diesel engine cylinder where the compression ratio is 25. And what that means, if you're not familiar with car terminology, is that if I look at the piston cylinder, if this is the initial volume, V1, when it's at the largest volume, and when it's at its smallest volume, if that is V2, the compression ratio is simply V1 over V2. So that right there is equal to 25. So that's what's known as the compression ratio. And diesel engines have pretty high compression ratios. 25 is not that uncommon. And what I want to know is, if the inlet, so the initial temperature is 25, what is the final temperature at the end of the compression process? So what we'll do is we'll go ahead and assume a constant heat capacity at this point and use this relationship. T2 over T1 is equal to V1 over V2, and the exponent there is K minus 1. And so what we're assuming is this compression process is isentropic. Now remember, in order for that to happen, there's two things that has to happen. Q has to be equal to 0, and it has to be reversible. So think about if that makes sense. Well, engines compress very quickly. In fact, you're running at hundreds to thousands of RPMs, and there's really not much time for heat transfer. So that's actually not a bad assumption to make. And reversible is in terms of if there's no heat transfer, we're talking about friction. So if this is a well-lubricated piston cylinder, that's a pretty good assumption as well. So isentropic compression in a diesel engine cylinder, or a car engine cylinder for that matter, is not a bad assumption to go ahead and make. So I'm going to go ahead and use this relation, and I've got this in specific volumes. This is in total volumes, but remember that the total volume is just m times v, and if I was to put that in, the masses are going to cancel out. So let's go ahead and use this value of 25 in here. It's just fine. So now I'm going to go ahead and solve for T2. T2 is equal to T1, V1 over V2 to the K minus 1. And recall K is equal to the ratio of the heat capacity, Cp over Cv. You can get those off of table A2. The third column over gives you the value of K. So go ahead and put our numbers in here. This would be 298. You need to be absolute temperatures here. And then my compression ratio is 25. And K is 1.4 for air. And I'm going to go ahead and subtract 1. And that comes out to be about 1080 Kelvin, which is 807 degrees Celsius. So it came in at 25, went up to 800 degrees. That's a huge temperature change. So there's a few things that we probably need to reevaluate in this problem. One is the fact that the heat capacity is probably not constant over that large of a temperature change. And the other thing, if you look at this value of K, again, if the heat capacity is not constant, K is also a little bit of a function of temperature, and I should have used a slightly different value than 1.4. But we'll go ahead and look at how we can go ahead and make this a more accurate answer than that. So for now, we have a ballpark estimate of 807 degrees Celsius. So if we wanted to go ahead and account for the variable heat capacity, okay, here's my TDS relationship, but I haven't assumed a constant heat capacity. And so if we remember, this is equal to S20 minus S10, the standard state entropies, minus R ln of P2 over P1. And if I go ahead and set that equal to 0, I can go ahead and rearrange this equation, and I find out that P2 over P1 is equal to the exponential of S20 minus S10 over R. So I just went ahead and moved the pressure to the other term and then took the exponential of both sides. Right? Now, this S20, that's just a function of temperature. So again, I have a ratio of pressures equal to some function of the ratio of the temperatures. And so if I define something called the relative pressure, this is P sub R, this is called the relative pressure, and as the exponential of S0 over R, that right there is simply says to something that's a function of temperature. And again, this is called the relative pressure, not to be confused with the reduced pressure when we were dealing with compressibility. And we're just defining it as this here. If I go ahead and put that into this equation here, I have P2 over P1 is equal to P relative to P relative 1. Things on the right-hand side are functions of temperature. They're just, I went and took the standard state entropy off of table A17, divided by R, and then went ahead and took the exponential of it. And these are actually tabulated in tables as well that we'll see, so that way we can go ahead and account for the heat capacity and get what our pressures are going to be. There's another one I can actually use. If I remember that, if I look at the combined gas law, P1V1 over T1 is equal to P2V2 over T2. I could go ahead and substitute that into this equation, and if I define something called the relative volume, and I'm going to go ahead and define that as P over P relative, I'm going to end up with another expression now which tells me that V2 over V1 is equal to VR2 over VR1. Those are relative volume, where relative volume, as I said, is P over PR, which if I put it into those other definitions, I have P over the exponential of S0 over over R. But everything there on the right-hand side is just a function of temperature. So again, I could tabulate these relative volume values by going to table A17, taking my S0 value, dividing by R, taking the exponential, 1 over that times the T, have this value. And now what I have is something that relates my volumes to something in terms of my temperature, and again, by accounting for changes in the heat capacity value. So let's go back and do this example now, but we're going to go ahead and account for this variable heat capacity. So again, I have this piston cylinder, compression ratio of 25. So I know that V1 over V2 is equal to 25, which is also equal to the specific volume of V1 over V2. And what I can do now is I know that that's equal to VR1 over VR2, where those are my relative volumes. And so where do I get those from? Now I'm going to go over here to table A17, and so if I look at this fifth column over, there's V sub R. In fact, there is P sub R. Those are the relative volume and pressure, all as a function of temperature. So I can go ahead and look that up, and we had our inlet at 298, and so my relative volume is 631.9 at the inlet. That's VR1. So if I come out over here, and I know that VR1 is equal to 631.9, those are unitless values. And then I'm going to go ahead and put that into here to find out what VR2 is. And VR2 is equal to VR1 over 25. So it'll be 631.9 over 25. And VR2 is equal to 25.28. Now this is just a function of temperature, so now I'm going to take this value, 25.28, go back to my table A17, and I'm looking for a value that's 25.28, and come over here, and it's somewhere right in there. So it's somewhere between 980 and 1000 Kelvin. So if I go ahead and do an interpolation in there, I find that the temperature is about equal to 1002 Kelvin, or about 729 degrees Celsius. So now put that in context. Last time we had 807 degrees Celsius. So this is about 70, 80 degrees different, which is not an inconsequential amount. This temperature is also slightly lower. Heat capacity increases with temperature. So therefore, by accounting for that, we're going to end up with a lower temperature with all of that work input.